Welcome to video 3.5 in our first Principles of Astrophotography series. In this video, we discuss opposition. That's the time of year at which a celestial object is opposite the sun in the sky.
At opposition, an object reaches its maximum altitude in the middle of the night and is therefore optimally placed for all night.
This video is based on section 3.5 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Bode Edwards.
Let's
talk sensor sensibility.
Principle 33, astronomical midnight. Astronomical midnight is the time at which the sun reaches lower culmination, its lowest point below the horizon. It does not generally occur at 12 midnight local time. Principle 34, opposition. A celestial object is at opposition and is well placed for nighttime astrophotography when it reaches its culmination altitude at astronomical midnight.
So we're making a distinction between 12 a.m. at night on your clock and astronomical midnight, which is halfway between when the sun goes down and when it comes up in the morning. That's not necessarily going to happen at 12 a.m. And the concept of opposition is really important. You'll see it in Telescopius and other software where you can just look up the opposition date of an object, and that tells you when it's going to reach upper culmination at midnight, the culmination altitude at astronomical midnight. And the other point to make about this is at astronomical midnight, that's when the sun reaches lower culmination. When we talked about in the last video, there's an upper culmination and a lower culmination for every object. And when the sun is at lower culmination, it's as far below the horizon as possible. That's where you want to be. Orion Nebula at opposition. So you can see here North America and South America. So we're looking at that hemisphere of the Earth. And we're thinking about looking at the Orion Nebula, which most people can see from almost any latitude. And here's our zenith, the point directly overhead, the north horizon, the south horizon, and the nadir, which is the point directly below your feet, right straight through the middle of the Earth. And when the Orion Nebula, is at opposition, then it is high in the sky at astronomical midnight. And that's where we want to be. I mean, here's the dark side of the Earth, the night side. Here's the day side of the Earth, and here's the sun. So the Orion Nebula is at opposition when it's on the opposite side of the Earth from the sun. So here's the sun, here's the Orion Nebula. You can see the Orion Nebula at night.
So you're saying if I was standing looking north-south, so standing looking south, and an Orion Nebula is at opposition at that exact time, I could follow straight up and find the Orion Nebula in the sky.
At astronomical midnight.
At astronomical midnight.
That's right. It's going to be right up there, its highest point. That's exactly it. So, just a reminder, in the last video we talked about the fact that 12 hours later, the Earth has spun halfway around on its axis. So, here's at astronomical midnight, when Orion's high in the sky at night. Here's at noon, 12 hours later, and I guess you'd call it astronomical noon, not necessarily 12 p.m., right? But 12 hours after astronomical midnight, the Earth is spun on its axis, and now you're seeing Africa and Australia and Asia, et cetera, and the observer, who was over here before, has now rotated with the Earth over to the other side of the picture as we look down on the spinning Earth. And So the Orion Nebula, the line to the Orion Nebula is this in the same direction. So it's down and toward the right in this picture. It's down and toward the right in this picture, but in this particular case, it's hidden behind the Earth. So, yeah, that's pretty much it. The sun is still in the same direction, but now this is the day side of the Earth, the lit side, and this is the night side. Just to emphasize the fact that objects rise and set during the day, seasonal objects at least.
Principle 35, astronomical night. Astronomical night is the time period during which the sun is at least 18 degrees below the horizon and the sky is fully dark.
So, astronomical midnight is at a particular time. It's the darkest part of the night. But actually, an astronomical night is a period of time between when the sun first, after the sun sets in the evening, the sun will be on the horizon, then it'll get lower and lower on the horizon. When it reaches negative 18 degrees, that's when astronomical night begins. And then it goes underneath the Earth onto the other side, and then as it's ready to rise in the morning, it'll reach again negative 18 degrees, and then beyond that, the sky won't be as dark. So this is full darkness when the sun is at least 18 degrees below.
Yeah. It's going to be different if you're in the wintertime or summertime, because nights are longer and shorter.
That's right. That's right. So you're going to have, we've noticed here at our latitude of 42 degrees in northern Utah and southern Idaho that, man, when you're near the June solstice, dude, I mean, you have like 4 hours of astronomical night.
Yeah.
And in the wintertime, for us, the wintertime in the northern hemisphere, at the December solstice, we get maybe something like 10 hours. I can't remember exactly.
Good.
You can just...
Yeah. Good time on target. Principle 36, opposition, right ascension. A celestial object is at opposition when its right ascension and the sun's right ascension differ by 12 hours. Kind of already talked about it.
Yeah, but the idea here is, remember in an earlier video we talked about right ascension, which is a full circle of right ascension is analogous to longitude on the Earth. And a full circle of right ascension is 24 hours, which matches the day. But it's just a way of measuring the right ascensions. This is the celestial sphere that we talked about in a previous video. This red line is the celestial equator, which is a projection of the Earth's equator onto the celestial sphere. This green path is the path of the sun across the celestial sphere. And here's this yellow dot is a position of the sun at the March equinox.
Yeah.
Then later, 3 months later, it reaches the June solstice. Then, roughly 3 months later, it reaches the September equinox. And then finally, the December solstice. And we talked about this in an earlier video. But the important thing to realize here is that when we talk about opposition, an object is at opposition when its right ascension and the sun's right ascension differ by 12 hours. All right, so let's say we're on March 22nd, the date of the March equinox, okay? And we want to know what objects are at opposition in March, when they'll be optimally placed. Well, you want to go around, halfway around to the other side of the celestial sphere to find those objects. So there's 1 hour, 2 hours, 3 hours, 4 hours, 5, 6, 7, and then right about here is 12 hours. So you want to look for objects whose right ascensions are at 12 hours if you're sitting at the March equinox. Yeah.
Principle 37, simple model of opposition. A simple linear model predicts the times of opposition of celestial objects to within 1.7%. These predictions are summarized in a simple wheel of opposition diagram that can be used to plan observations.
So we took some data from a NOAA, National Oceanic and Atmospheric Administration.
Nice.
Model of the movement of the sun, of the right ascension of the sun. So this represents the right ascension of the sun as a function of the time in days minus the time in days of the March equinox. So what that means, if we take the difference between those, if the time we're looking at in days, starting from the beginning of the year, and we subtract the time in days of the March equinox, which is roughly 3 months, because it's from January to March, then if the time that we're looking at equals the time of the March equinox, then T minus Tm would be 0. So this would be the position of the March equinox. Okay, so then this blue dotted line is the NOAA model of the sun's right ascension. It's not a straight line. The red line is a straight line. It's our model. It's a simple model. And the most that these two differ from each other is just about like 1.7%. So our model there's nothing fancy about it. It's a simple linear model of quite a nonlinear. The reason the sun doesn't follow a nice straight linear line is because the Earth's orbit is elliptical, and I think that's the main reason, which causes the sun, from the Earth's perspective, to move across the celestial sphere not in a nice linear way.
Yeah.
So this is the right ascension of the sun on which our model is based. And so basically what we're saying is that an object that is at opposition, if the right ascension of the object is 12 hours different from the right ascension of the sun, then that's when you have opposition.
I'm not opposed to that.
I'm not opposed. That's good. So this is the actual linear model. This is the time in days. At opposition. So the time can be t equals 0 on January 1st, and t equals roughly 365 days on December 31st, right? So we're just talking about measuring time in days from the beginning of the year, not splitting it up into months or anything fancy like that. Just makes it easier that way. So it looks like by linear, we usually think about y equals mx plus b, where b is the intercept, m is the slope, y is a function of x. Here we have t, which is replacing y, is a function of alpha, and alpha here is the right ascension. So you can plug in the right ascension of any celestial object. You look it up in Wikipedia or wherever your favorite place is to find right ascensions. Plug it into this model, and that gives you the time in days at which that particular object is going to be at opposition. So let's do a couple of examples. The Orion Nebula, its right ascension is 5.58 hours. So we plug that into the formula we just wrote down. That's the right ascension. Just double check here. We got right ascension right here, 24 hours right here, then 365 days. Here's the right ascension. There's 24 hours, 365 days. The hours cancel. We end up with 364 days. And if you work that out, that comes out to be December 12th. If you count how many days there are in January, how many in February, et cetera, et cetera. And most people, well, a lot of you know already that the best time to go looking at the Orion Nebula is in December, right? So that conforms with what we're talking about. I'll talk about this wheel in just a second. Bode's galaxy. It has a right ascension 9.9 hours. Plug that into that formula. You get 412 days, which is kind of embarrassing. Because 412 days, that's kind of more than the number of days you have in a year.
That's a day.
It's
a
super
year and a
embarrassing.
bit. Yeah.
Yeah. And so what you do is just subtract 365. The formula, you have to manually subtract 365 days to
You
be
need
able-
an absolute value in there somewhere.
Yeah, somewhere. Yeah, or actually you need a mod function. And in our book, we talk about the mod function that you can use and to do these calculations. So for Bode's galaxy, it has a right ascension of 9.9 hours. That's roughly 10 hours. So these blue numbers around here are right ascensions. And the red marks here are the first of the month. So this red mark here corresponds to January 1st. This red mark corresponds to February 1st, etc. So January is going around this way from the 1st to the 31st. So we're looking at February 16th. Well, here's February 1st, here's March 1st. So February 16th is going to be roughly right about here. And that corresponds roughly with the right ascension of 9.9. So probably the easiest, the most useful way of putting together, of using this wheel, if you don't want to use the equation here, which is a bit of a pain, you can use this, what we call a wheel of opposition, that you'd say, all right, I know I can look up Bode's right ascension. It's 9.9. I go out here, I try and find the right ascension out here in blue that's around 9.9. So 10's pretty close to that. That just basically says that in the middle of February, that's optimal time for looking at Bode's galaxy. So, you know, normally in our observing, the clouds are going to roll in on February 16th, or the moon's going to be full, or whatever. And so no big deal, as long as you're somewhere in that vicinity. It could even be in mid-January or mid-March. It'd be close enough to get a good shot at Bode's galaxy, as long as its culmination altitude is high enough for you to get some data. So honestly, you can do more accurate calculations of the opposition of objects than this wheel provides, but who cares, right? You're not going to probably not. I mean, you might have personal obligations. You might be traveling on that night, or the clouds might be there, and so plus or minus a month, it just gives you a good idea about where you need to be. If we want to look at the Orion Nebula,
Well, most people just want to know if they can if you can get that
Get some-
object and when we should get that object.
yeah, when
Not the day.
the particular day. Yeah, exactly. So doing another example, Orion Nebula has right ascension of 8 hours. So here's 5 hours, here's 6 hours, so somewhere around here, right? So for the Orion Nebula, like we talked about, somewhere between December 1st and January 1st, somewhere mid-December, it'll be great time to see. Yeah, so we think the wheel of opposition might be a useful tool. In our observing target list, we have opposition dates calculated for using this formula, calculated for all the objects that we're interested in. So,
You might say it's the wheel of time for astrophotography.
speaking of Brandon Sanderson, right? Isn't that the Wheel of Time? The
He
Wheel of
finished
Time.
it. Yeah.
What do you mean he finished it?
Well, he didn't start. He wrote the last 3 books in the
Oh, who was the Wheel of Time?
Oh man, Robert Jordan.
Oh, Robert Jordan.
Yeah.
Cool. Yeah. So thanks so much for watching.
And we'll see you next time.